I guess many of you are a bit horrified by the horrifying big equations in this subject. However, I can tell you that behind each and every such equation there is a nice picture, nice movie. Today my motto is to uncover some of those pictures behind these horrifying equations. Let us begin. Okay, suppose this is an LTI system. Input X, output Y, and the impulse response of this system is denoted with h of t. Impulse response of an LTI system is its characteristic property, so that if you know how impulse response looks like, then you know everything about that system. Because if you apply any arbitrary input under initially relaxed condition, then you can calculate the output using this formula: output equal to the convolution of input and impulse response. So knowing impulse response means knowing everything about an LTI system. Now suppose for this LTI system the impulse response looks like this. It is initially higher, it has a value of 3 at time equal to 1, then it gradually decreases and becomes 0 at t equal to 4. I have intentionally taken it to be piecewise constant for ease of understanding, and I have intentionally colored the area under it with a yellow color. Now suppose some arbitrary input is applied to this system, which looks like this. It is initially lower, then it increases, then it decreases, and finally becomes 0. Once again, for ease of demonstration, I have taken it to be piecewise constant, but it could be any continuous arbitrary input function in principle. Now this is the input applied to the system, and our goal is to find the effect of this input, effect or output corresponding to this input is what we want. So let us calculate that. For that, we shall chop this input into very narrow slices. Let me take a graph paper. Now let me slice this input into narrow slices like this. Okay, so this is one slice, this is another slice, another, this is one, this is another, and so on. Let me call these individual slices as A, B, C, D, E, and F. Now to find the output corresponding to this input pattern, what we shall do is this. We shall find the output corresponding to these individual slices and then we shall add those outputs. So let us do that. Consider slice A. And one more thing, you should remember that when these slices are very narrow, that means the delta time interval between two slices, if that is very narrow, then these individual slices can be considered as impulse signals, and the strength or the coefficient to those impulse signals depend on the area under this individual curves or the area of these individual slices. Okay, so let me begin with slice A. This is an impulse occurring at time equal to 1, and the area of this is 1. So the output corresponding to this part will look like the impulse response or the response corresponding to an impulse, which we already know, which is given here. So let me copy this and let me put it here at this position. Okay, this input impulse occurs at time 1, therefore the origin of HT, this point, should come at time 1. So this is the output corresponding to the input, the portion of the input A. Now let's come to portion B, part B, that is again another impulse of unit area. So its response will again be similar to this graph. So I will copy it and put it here. After 1 unit delay from the previous output, this is the output corresponding to portion B. Then for portion C, I will again copy this, but this time I have to increase the height by a factor of 2, like this, because the area under this impulse is double. Now I shall put it here. This is the output corresponding to part C. Then for part D, I will take another copy of this and put it here. That is for part D, and so on. After that, you have to add all these cards together, and I am leaving that addition for you. Let us consider only one slice of the input and the effect of that one slice. Consider slice A. Slice A is so narrow, so thin, that it occurs at one point of time, at one particular instant of time, but its effect lasts for a longer duration depending on the width of the given impulse response. So this slice of input occurs at this point, however its effect starts here and completes at this point. Similarly, consider another slice, maybe slice C, and the effect of slice C starts at this point and finishes here. So this point of time will be affected by both slice A and slice C of the input. And let me now ask a very interesting question. The question is, how much is the total effect or total output at a particular time instant? Say call it T. Suppose that point of time is here. Suppose this is our T, and we want to know how much is the total output or total effect due to all different slices of the input. Note that this point, which means this point of time will be affected by slice A, slice B, slice C. However, slice A will have lower effect at this point of time compared to slice B, because as per the given shape of the impulse response, the effect of input decreases with time, and this point of time is farther from slice A compared to slice B, so slice A will have lower effect at this point compared to slice B. And to find the total effect at this point or at this point due to all the different slices, we will use a clever trick, and the trick is as follows. We will copy this impulse response and flip it horizontally. That is a time reversal, and when we flip it, make sure that the point which was at t equal to 0, that is not moved. Okay, so that point I have marked with a red line to make sure that is not moved. Next, if I want to know the total effect at this point of time, then I will bring this flipped impulse response and put it below the input curve in a way such that this red marker is directly below this point of interest, time t. So if I want to know the total effect at time t, I will put this red line, red marker directly below this, and this red marker is actually originally this origin t equal to 0 of impulse response. After this, okay, and let me put the values. This is 3, 2, 1 and 0. Okay, now after this, to calculate the total effect at this point, I will do it this way. The total effect will be 3 multiplied by the strength of this slice C, plus 2 multiplied by the strength of slice B, 1 multiplied by strength of slice A. So the total effect at T is 3 multiplied by the strength of C, slice C, plus 2 multiplied by the strength of B and 1 multiplied by the strength of A. So at this point of time, slice A will have effect proportional to 1, slice B will have its effect multiplied by this factor 2, and slice C will have maximum effect at this point because this point is closest to slice C. This is the total effect at this point of time. And by strength, I mean the area of the slices. So strength means here the area of that input slice. Now suppose I want to calculate the total effect at a different point, maybe here. Suppose now this is the time instant where I want to calculate the total effect. So that point is here, and to calculate the total effect at this point, all I have to do is to move this pattern here directly below the point of interest. This red marker should be at the point of interest, and then now I can calculate the total effect as 3 multiplied by the strength of E. Let me write this in green color. So for this new time instant, the total effect will be 3 multiplied by E, then 2 multiplied by D, and 1 multiplied by C. So this is how we aggregate or accumulate the effect for all different slices of the input. And if you change your time of interest, all you have to do, you have to move this pattern left or right and put it directly below that point of interest. Now in this demonstration I have one mistake, one problem, that is these slices that I have taken, they are not infinitesimally small, infinitesimally narrow, and therefore when you sum the effect of these slices in this way, you will get some error. To get perfect answer, you should take very thin slices, and therefore the number of slices will also be very large, and then this sum will actually turn into an integration. Now I shall tell you the exact process how to do that with another example. This example was to give you the idea how to flip this impulse response to get the total effect, aggregated effect at any particular time instant. The underlying idea is somewhat like this. Suppose X unit of rain on a particular day, say Sunday, produces Y unit of moisture after 3 days, that is on the Wednesday, and Y is given by the amount of rain multiplied by some constant H3. So I am saying that X unit of rain on a particular day produces H3X unit of moisture after 3 days, and if that is the case, and if climate is a linear time invariant system, then converse is also true. That is, the amount of moisture on a particular day, Wednesday, due to the previous rain is given by H3 times X, that is H3 times amount of rain 3 days earlier or 3 days before. That's the idea. Now let us take another example. Suppose two signals are given to us, HT, which looks like this, and XT, which looks like this. These are given, and the question is to find and draw YT, which is the convolution between X and H, which can also be written as the integration of X tau H t minus tau d tau, tau running from minus infinity to plus infinity. Our goal is to calculate this convolution and draw how y will look like as a function of time. Okay, so first of all, you observe that in this integration, tau is the running variable, t is not the variable of integration. T is like a constant when we carry out this integration. So let us first draw X and H as functions of tau instead of t. For that, let me just erase this t and put tau here as well, h of tau, here x of tau and tau. So now x and h, they are drawn as a function of tau, not t. Okay, so we need x tau, which is here, and we need ht minus tau, which we shall find. Okay, for that let me take a graph paper. we shall first draw h minus tau from h tau, and after that we shall draw h of t minus tau. This is a time reversal of this signal, and then this will be a time shifting. Okay, so let us first copy this. So this was h tau, and now I flip it, keeping the origin at the same position. So this is h of minus tau. Next we need h of t minus tau. Okay, for that we have to shift this signal or time shift this signal. Note that to come from here to here, what I have to do is we have to replace tau with tau minus t, because in this expression h of minus tau, if you put here h of minus of tau minus t, then this is equivalent to h of t minus tau. That is what we want. So we are replacing tau with tau minus t, and that means this will be a time shift by an amount of t towards the right. So this pattern is to be shifted towards the right by an amount of t. Now suppose t is here. T is an arbitrary number, so it can be anywhere. Let's say t is here. If that is the case, then we will move this signal from here to here, such that the point which was at origin comes from origin to time equal to t. So that point I have marked as with a red line. So this red line should go to the point wherever this t is. So this is ht minus tau. After that we have to multiply these two. X tau is here, ht minus tau is here. Now we have to multiply these two signals. Let me do the multiplication here. So I am going to draw x tau h t minus tau as a function of tau. If you multiply this signal with this signal, the result will be 0 from minus infinity to up to this point, and after this point t, again the result or product will be 0, and within this small region the product will be non-zero. So let me draw from minus infinity to here, product is 0, then from this point t, which is somewhere here, after this point the product is again 0, and between these 2 points the product will be this signal multiplied by this signal. Now this is a constant equal to 2, So I shall simply multiply this signal by a factor of 2, and that will look somewhat like this. Okay, and then this is the product. This is the time t. Now next thing that we have to do is to integrate this signal or to calculate the area under this curve, and that will give the value of yt at this particular time instant. Now to get the output at a different time instant at a different value of t, suppose t is somewhere here, all we have to do is to move this signal to this point like this, bring it here, then multiply these two signals and calculate the area under the product. This way we can calculate the output at different time instants and draw how yt varies with time t. Let us draw yt now. Let me draw yt here as a function of time t. Okay, so for that you observe, if time is less than 0 somewhere here, then to find the output we have to keep this signal somewhere here, and then ht minus tau and x tau has no overlap, no common portion. Therefore, the product of this and this to x tau and ht minus tau will be 0 and yt will also be 0. Therefore, I can say that output will be 0 if time t is less than 0. After that, as time increases, this signal is to be moved towards the right, and then it will have some overlap with x tau, and when you take the product will be non-zero in this region and you will get some area under the product. So output y will be non-zero, and as time increases, t increases, you have to move this signal towards the right more and more. So overlap between this and x tau will increase. So the area under the product of ht minus tau and x tau will increase. So output y will increase. So as time increases, output y will increase. Okay, so output will increase like this. At this moment, when this red line is at t equal to 2, that means t is equal to 2, then the overlap is maximum between x tau and ht minus tau. Okay, so the value of y will be maximum at t equal to 2. How much will be that value? So let us multiply this with this and calculate the area. Now this is a constant, so I can calculate this area and multiply that with 2. Now this area is how much? This is 2 into 1 divided by 2 because of the triangle. So this area is 1, this is 2. So the area under this product at t equal to 2 will be 2. So yt will be equal to 2 at time equal to 2. So let me draw it approximately. So y will increase and look like this. After that, as time increases, you move this pattern further towards the right, and therefore the overlap between x tau and ht minus tau will decrease. Therefore value of yt will decrease, and then when you move it quite far at this point t equal to 4, then there is no more overlap, and therefore the output will be 0 at t equal to 4. Let me extend this to t equal to 4 and a little more. Okay, so at this point output will decrease and become 0. So output decreases. Let me draw it approximately. It will come down and here it will become 0. So it goes up like this and then comes down and then becomes 0. This is the output pattern. Let me summarize these steps. Step 1, to draw x tau and h tau, which is by simply replacing t with tau. Next, draw h minus tau. Next, draw h t minus tau. That is what we have done here. Next, multiply x tau and h t minus tau, and finally calculate the area under this curve, or integrate x tau h t minus tau, and then you vary the value of time t to get the output at different time instants. Now I will tell you some important formula about convolution, which I will tell you. Before that, let me define a term called support of a signal. Suppose a signal looks like this. It is 0 here up to this point, then here it is non-zero, and then it becomes 0 again. So this signal is non-zero within these two time limits. Call it t1 and call it t2, x of t as a function of time. Now the support of this signal means the area time interval where this signal is non-zero, which is from t1 to t2. So the support of this signal is from t1 to t2, or maybe we can write it this way. This is t2 minus t1, where this signal is non-zero. Okay. Now an important rule is this: if you have two signals xt with support say from tx1 to tx2 and another signal h of t with support from th1 to th2, then if you convolve these two signals, then the support of y, or the result of convolution, will be from tx1 plus th1 up to tx2 plus th2. Just add the supports of these two individual signals. How can we justify this? So let us go back to this demonstration, and here suppose this xt has a support of tx1 up to this point, tx2. So this is the support, and for this signal, say this is the support is th1 and th2. Now when you convolve x and h, then portion A will have its effect from here to here. Okay, so the effect of A lasts between, so this part A, when this is very narrow, if you slice them with very narrow slices, then A is at point tx1. Okay, so A occurs at tx1, and therefore the effect of A lasts between tx1 plus this time from here up to tx1 plus this time th2. So this input occurs at this point tx1, and its effect is from tx1 plus th1 up to tx1 plus th2. Similarly, effect let us consider the extreme end of this signal f. F occurs at tx2, and therefore effect of f lasts from tx2 plus th1 up to tx2 plus th2. And similarly for all other intermediate portions, their effect will last from some point between these two extremes. So this is one extreme and this is another extreme. All effects due to all other portion will lie between these two times, because the effect of the first part is here and the effect of the last part is here. Effect of any middle part will be somewhere here. So this is one extreme, this is another extreme. This is tx1 plus th1, and this point is tx2 plus th2. Now another very interesting rule. Suppose yt is equal to xt star ht, then the area under the curve yt, which is integration of, let me write it verbally, then the area under yt will be equal to the area under x multiplied by the area under h. This is very easy to prove mathematically. The area under yt is the integration from minus infinity to plus infinity y of t dt, and this can be written as, in place of y I will write the formula for convolution, which is x tau h t minus tau integrated from minus infinity to infinity. This integration is over tau d tau, and then this integration is this integration which is over t dt. Now let us swap the order of integration. Let us first integrate over tau from minus infinity to infinity, then from t equal to minus infinity to infinity, x tau h t minus tau dt, then d tau. So first integration is over t, then over tau. Now you note that while doing the inner integration, this is constant, x tau is constant because t is the variable. So therefore we can take x tau outside of the inner integration. Then it becomes x tau, then t equal to minus infinity to infinity, h of t minus tau dt, and d tau. Now you can readily see that this is the area, this part is the area under H. Or to be more rigorous, if you want, I can replace t minus tau with a variable, say z, and then it will become like this. Then integration of h of z, I am putting t minus tau is equal to z, such that dt is equal to dz, and here I write dz. The limit of integration will remain z equal to minus infinity to plus infinity, and then d tau. Now this is the area under H, and you can take it outside, or you may write it this way, d tau here. So then this is the area under H and this is the area under X. So this becomes area under X multiplied by the area under H. That's the proof. But beside this mathematical proof, there is a more interesting way of visualizing this. A more interesting picture is like this. Okay. When we calculated this convolution or the output, what did we do? We chopped the input into narrow slices and calculated the output for each of the slices and added them all. So let me call the effect of A as, say, A prime, that is this part, the effect of B as B prime, effect of C as C prime, and so on, D prime, E prime, F prime. Then we need to add A prime plus B prime plus C prime plus D prime plus E and F prime to get total output YT. So this implies that area under YT will be the sum of area under A prime, this part of the output, plus area of B prime plus up to area under f prime, all of them. That is the area of y. Now how much is the area under a prime? Okay, or let me consider say area under c prime. So let me bring it out. So this is c prime. This is the effect due to this particular impulse. Okay, so how much is this area? This area is the area of h multiplied by the strength of this impulse. Okay, so in this case this is 2 unit. So we therefore multiplied this h by a factor of 2 to get this output. So area under c prime can be written as the strength or area of input c multiplied by area under h. Similarly, area under b prime will be strength or area of b multiplied by the area of h. So in this sum, area of h is common. So I can write it this way: area of h multiplied by the sum of area of a plus area of b, c, so on up to area of f. Now this sum is nothing but the area under the input. So this becomes area of h multiplied by the area under x. Next, I will tell you a couple of very important rules or formulas. First of all is like this. Suppose x is an arbitrary signal. X of t, some arbitrary signal you imagine, and we want to calculate the area under this curve from minus infinity up to some point of time. Okay, suppose some chosen point of time is here, call it some arbitrary time t. We want to calculate the total area under this curve from minus infinity up to this point. Then that area, if we call that as y of t, which is the area under x from minus infinity to time t, then that you may write it this way, x integrated from minus infinity to time t. This area is given as the convolution of x and u, where u is unit step function, step signal. Okay, and if you change the value of time t, say you change it to this point, this is t, and you want to calculate the total area from minus infinity up to this point, that is the value of yt. So you can vary this time t, and therefore the area will also vary. And we can plot the area as a function of time t. That plot, that area as a function of time is given as x star ut. What is the proof? Proof is very simple. We know that x star u is given as x tau u t minus tau d tau from tau equal to minus infinity to infinity. However, we know that value of u will be 0 if this argument is negative. That means if tau is greater than t, then this is negative and u will be 0. So I need not carry this integration over the entire range. I can carry this integration only tau from tau equal to minus infinity up to t. If tau becomes greater than t, then this will be negative and u will be 0. If tau greater than t, then u t minus tau is equal to 0. So I will integrate only up to time t, and before time t I know the value of u is 1, and this is what we wanted to prove. Okay, but there is a nice visualization of this formula, and you can visualize it in this way. Let me draw u as a function of time. So we know that u looks like this. This is ut or u tau. It is 0 here and 1 here. Now to get u minus tau, you may just flip it like this. This is u minus tau, and then to get u t minus tau, you have to shift it towards the right, so that will look like this. You shift it up to some time t, so this is u t minus tau. Then you multiply this signal with x tau maybe, and when you multiply these two, then the result will be like this. It will be like x up to this point of time. After that it will become 0. So it will remain non-zero up to this point of time only, and when you calculate the integration, you will get the area up to this point. That's how to visualize this formula. Now I will tell you another very important formula, which is this. Given any arbitrary function x, if you convolve this with delta t, the result will be x itself. Proof is very simple. X star delta is same as x tau delta t minus tau d tau, tau running from minus infinity to infinity, and this you can also write as x of t minus tau delta tau by virtue of the commutative property of convolution. And then we know that when we multiply any function with delta function and integrate, the result is same as the value of this function evaluated at tau equal to 0. So you put tau equal to 0 in this function, you will get x of t, and that's the proof. That's the proof. Okay. However, there is a very nice visualization of this fact. For that, we have to go back a bit. Recall that we said a few days back that any signal can be chopped into narrow slices, and then that can be written as the sum of these individual slices, and when these slices are very narrow, then they behave like impulse signals. So any signal x can be written as the sum of these chops, these slices, when the delta t, the width of the slices, tend to 0. And then the slices are like time shifted impulse signals, which you can therefore write as xt equal to integration of x tau delta t minus tau. And when we told this relation, this formula, at that point you probably did not know that this is also the formula of convolution between x and delta. So the convolution between x and delta is same as x itself, and this comes from the fact that any signal can be written as the sum of small narrow slices like this. Now the last thing that we will discuss today is about invertible and non-invertible systems, which I forgot to tell you before when we discussed different classes of systems. Let me define. Given a system with impulse response h1t, if we can find another system with impulse response h2t such that h1 star h2 is equal to delta t, the result of convolving h1 and h2 is unit impulse signal, then what will happen? Then if we connect these two systems in cascade like this, given system h1 followed by another found system, h2, connected in cascade. Xt comes here. Output goes to the input of the second system, and here is the final output. So here we will have x star h1, and here we will have x star h1 star h2. Now h1 star h2 is same as delta, so we will have xt star delta t, and x star delta is same as x. So that means whatever input you give, you get the same thing as the output. So whatever modification the first system does, that is undone by the second system. So we will call the second system as the inverse of the first system, and we will say that this system is invertible. So then we say the given system is invertible, and the second system is the inverse of the given system, or they are inverse of each other. Okay, and if you cannot find such system, or if nobody can find such system in theory, then we will say this system to be non-invertible. Let us take an example. Suppose a system behaves in this way. Output is equal to input squared. So if you give one, or say if you give 2, you get 4. If you give -2, you also get +4. Now can you find another system which will take this 4 as the input and give you back the original input 2 or -2? That is not possible, because how will this second system know whether the original input is +2 or -2? It's not possible. So this is a non-invertible system. No one can find a system which will take 4 as the input and tell whether it came from +2 or -2. On the other hand, some very easy example of invertible system could be like this. Suppose you have a system where y is equal to 2 times x. Then you can always find another system where y output is equal to input divided by 2. Now if you connect these two systems in cascade, input is given here, it is doubled, and then it is given to the second system. Here output will be same as the input. So this is a invertible system, and these two are invertible pairs.